Where are you going?
Hey guys, I'm Cam. I'm going to be talking about the Sydney Quadcopter and specifically about architecture from both hardware and software point of view. So the primary motivation of building the Quadcopter is to help us understand how the practices that we use every single day on a ThoughtWorks project can apply in the hardware world. So how do we take blue-green deployment and apply it to a quadcopter? How do we take infrastructure as code and apply it to a heart rate monitor that might be strapped to our chest? If we understand this, we can build new capabilities in ThoughtWorks, which will hopefully diversify our work and our impact. The problem we're trying to solve with the quadcopter is delivering beer. Quadcopters are an interesting solution for this because they're good at traveling long distances, they're good at carrying small loads, they're good at accessing otherwise inaccessible places, such as high places or dangerous places, and the person grabbing the beer at the end will have to be very careful they don't get their hands chopped off by the propellers when they're getting the beer. To generate lift, we need propellers. The propellers we've chosen are 10 inches long and cause a displacement of 4.5 inches for every complete rotation they make. Given they'll be making 200 complete rotations per second, roughly, we expect this to generate about 600 to 800 grams of thrust, which, given we have 4 propellers, should be enough to lift our 1.5 kilo-ish quadcopter with a small payload. Quadcopter test. What happens when we stop the propeller? That's not too bad. We will be using brushless motors to rotate the propellers. A brushless motor consists of a case, a shaft, and a series of electromagnets. A propeller will be attached to the shaft. Turning the electromagnets on and off really quickly will cause the permanent magnets attached to the case to rotate around it. Can you change the speed?
Oh yeah.
Wow, can you turn it off?
Can you do like the tiniest amount?
I'm doing it slowly.
Okay.
As the motor starts to spin, the electromagnets must be turned on and off at exactly the right time so the motor doesn't suddenly jolt to a stop. This responsibility is handled external to the motor by something called an electronic speed control. The ESC expects a digital signal representing throttle. A microcontroller will be used to send the signal. A microcontroller is a tiny computer that fits on a single integrated circuit. It has a little CPU, a small amount of RAM, some flash. It uses very little power, which is perfect for controlling embedded devices. Our microcontroller will receive throttle from a remote control receiver. The remote control receiver listens for throttle signals sent over the 2.4 GHz ISM band from a handset where a user has a throttle joystick. Are you ready?
Yeah, let's wait.
Just wait.
Ready?
Yeah?
Yep. And then get back. That's definitely necessary. Ready?
Yep. Wow. To fly level, the quadcopter adjusts individual motor throttles based on its angular position. We measure this using the combined output of an accelerometer, a magnetometer, and a gyroscope. We will also use a barometer to measure altitude and a GPS to determine location and time. Everything is powered using an 11-ish volt lithium polymer battery. Its high energy density is great for flying, however they can be unstable, which is why commercial airlines don't like them very much. Power is split in parallel to each of the ESCs. Each ESC contains a voltage regulator, outputting constant 5 voltage and converting excess voltage to heat. This is terribly inefficient, so I'm going to start every component that does this. This regulated 5 volts that comes from the ESC is what's used to power the microcontroller. The ESCs then power the motors as they control them. Then the sensors are powered by the microcontroller on a power output pin, as is the remote control receiver. The software of a quadcopter is basically a loop that runs forever. Every iteration of the loop first reads sensors, does some kind of calculation, and then writes new throttles to each of the motors. In order for the quadcopter to be able to adjust to wind and other flight situations without falling out of the sky, we need to go through this loop about 400 times per second. $25? You still got heaps more time, space. The first choice we have is about deciding the control system, which would typically be a microcontroller. One option we have is we could use a Linux processor, such as that on a Raspberry Pi. The problem with a Raspberry Pi is it consumes a lot of power, around 700 milliamps, which is around 100 times what you would normally find on a microcontroller. Also, with Linux, at any time the operating system may switch out your quadcopter process. That makes it highly unlikely that it will run the 400 loops necessary to keep in the air. Another option is to use a high-power microcontroller that has an interpreter running on it that interprets a more interesting language. So I've seen interpreters for Brainfuck, Python, the JVM, although I wouldn't expect Scala or Clojure to work on those JVMs because they don't implement the full specification. There's Clojure that compiles to C, but I don't really want to compile. Node.js depends on V8, which is a beast when it comes to memory. Ditto Haskell, Erlang, Go, Scala. They're theoretically possible, but at the moment not practical. Recently there's been some interesting things come out in the JavaScript world. First there's the Tessel, which runs Node.js compatible JavaScript using a Lua runtime. It has its own hardware module system, which is why we're not using it. The second, and the one we've chosen, is called the Esperino. It's basically a JavaScript interpreter that runs on a pretty standard microcontroller. It comes with a development board which gives us access to the pins, and a whole bunch of libraries which makes interfacing with hardware easy. One of the challenges we have with using JavaScript in this way is that most JavaScript libraries expect either a Node.js ecosystem or Windows, or a browser ecosystem. We have neither when we're running on the Esperino. So we've had to write our own code to deploy to the Esperino, and we'll probably open source this at some point. We've also had to write our own testing libraries that actually execute on the Esperino. We feel this is important because the JavaScript interpreter is so immature that regular expressions, exceptions aren't even implemented. And you'll notice we're uglifying, and that's because whitespace on the JavaScript interpreter actually makes the code execute slower. We achieved a milestone the other day when we got our tests running on the Esperino for the first time. We then fried our chip moments later. So now we're waiting for the next Esperino to be delivered, and then we can get on with building the quadcopter again. We want blue-green deployment, so we can add a Linux processor that's Wi-Fi enabled. When we deploy over Wi-Fi, the Linux processor will push the code to the microcontroller. If the code is bad and the quadcopter starts falling out of the sky, the Linux processor will recognize this using freefall detection in an accelerometer. It will then revert the code, hopefully fast enough so that the quadcopter hasn't already hit the ground. We want the quadcopter to be able to follow someone. We'll attempt to do this by using an iBeacon held by a person. On the quadcopter there will be multiple Bluetooth devices. By measuring signal strength at each of these devices, we should be able to triangulate the signal of the iBeacon and therefore follow it. We want real-time analytics for things like voltage, current, battery, throttle, position, angle, etc. Some of these values will change every 20 milliseconds or so capturing it all is going to be a challenge. We don't know how to do this yet. So we just bought an Oculus Rift. I don't know what we're going to do with it yet, whether we'll attach it to the quadcopter or not. So if you want to come and play with it, come and find us. No, but we can't control it. So if it goes up. Brace.
At what point does it lift?
I don't know. It's the second time we've done it.
So it's there, let it go.
That's it for me, guys. Thanks for listening. Please send any questions to cam.swords@gmail.com, or you can follow our code on GitHub.